Hello everyone. So today we're going to talk about our last example in 14.7. I will definitely hoping this is our last video. I definitely don't want to split this example into two videos, so I'm going to try to squeeze that into one video. So let's get to it. So here's our next example. See, our last example right here, this one, which is y double prime plus y equal to x squared, definitely can be solved without using power series. We can probably use the characteristic root to solve for the homogeneous solution, and then to get the particular solution with x squared, we can probably just use the undetermined coefficient methods, which would definitely be able to allow you to come up with the same exact solution right here with probably less amount of work. So obviously we're not doing this type of problems using power series. So how about let's look at a problem that we actually have to use power series to come up with the solution. Okay? Alright, so let's try an example where we won't be able to use any method that we know to deal with it. So how about we do this one? Given y double prime plus xy equal to negative 2x plus 3x squared minus x to the fourth. And we're going to try to go through the following. Part A, we're going to use power series to find the homogeneous solution. And then we go use the power series to find the particular solution. And then we can combine them together to find the general solution. All right. So once again, this problem should hopefully work out nicely. Hopefully, unless we make some mistake. But if not, it should work out quite nicely that we can pretty much do the same thing like we did before. Remember what we did before is that we run to this choice right here where we're to pick the easiest choice to generate the solution. And the key is to try to make as many of these coefficients, c sub 0, c sub 1, c sub 2, c sub 3, c sub 4, so on and so forth, to equal to 0. So that I can form the particular solution easily without going through another power series. So in here is just simply try to set as many of them as 0 and only try to focus on the fewest number of c sub k that doesn't have to be 0 to satisfy all of this equation at the same time. Okay? So that's the basic goal. So let's see if we can do that in here. So first of all, let's start with our homogeneous solution first. So we're going to let y equal to summation k from 0 to infinity, c sub k, x to k. And we already know what y double prime is, so I'm just going to write out my y double prime, which is k from 0 to infinity, c sub k plus 2, k plus 2, k plus 1, x to the k. So now my homogeneous differential equation is y double prime plus xy equal to 0. So now this x right here is really going to screw us up because it messes up our x to k. That's the problem. So let's see how that works. And let's see if we can, and I'll show you how to deal with that. So here's my y double prime. So the problem right here is that this x is going to be distributed inside, and therefore turning this into, how should I write it? I'm going to just cross this out, and say x to the k plus 1. So now that become a problem because now I have a mismatch in our exponents. So how do I fix it? So one way to fix it is, once again, by reindexing. So how do I reindex this? So let's show you. So the first summation stays the same. I can't really do anything with it, nor do I want to do anything with it. what I want to do is reindex so that I can have k to the x to the k power. So if I look at this right now, if I start with k equal to 0, then our first term would just be x to the first power. So that would mean that it's the same thing if I say k from starting from 1 and I have x to the k. That will also give me the first power. The problem is if I look at the top summation, when I plug in 0, I start with c sub 0 term. So to fix that, we'll put c sub k minus 1. That way when I plug in 1, I will get c sub 0 term, and I'll get kx to the first power, which is exactly the same as if I would plug in 0 in our first summation of k from 0 and then c sub k x to the k plus 1. So that's how I fix it. But of course, now I create a new problem. The new problem is we don't start the same exact beginning index. This one starts k equal to 1, this one starts k equal to 0. So what I'm going to do, just like we did before, I'm going to pull out the k equal to 0 term. So if I do that, I would have c sub 2 times 2 times 1 x to the 0. Ooh, actually, I'm going to need more room. I'll go right here. C sub 2, 2 times 1 times x to the 0 plus, and I now can combine these two summation together, starting with k equal to 1. Then I have c sub k plus 2, k plus 2, k plus 1, plus c sub k minus 1, multiplied by x to k equal to 0. So now I can try to form all these terms. So what would happen is this gives me two equations. The first one is c sub 2 times 2 times 1, so I'm going to say 2c sub 2 is equal to 0. And then c sub k plus 2 times k plus 2, k plus 1, plus c sub k minus 1 would also equal to 0. So that gives us these two equation. So notice that this first one would tell me that c sub 2 must equal to 0 to begin. No other way. The second one tell me that c sub k plus 2 should equal to negative c sub k minus 1 over k plus 2, k plus 1. Now, if you don't like the fact that we have negative c sub k minus 1, which actually I don't like it either, I could reindex it. Okay? And the way to reindex it is to do the following. I would say that's just the same thing as c sub k plus 3 equal to negative c sub k over k plus 3, k plus 2. So notice that if we use c sub 0 in the formula, okay, or in this case, let's say I put 1 in for k for the first formula right here. I have c sub 3, and I have a negative c sub 0, and I have 3 times 2. It will be the same thing as if I use the second formula and start with k equal to 0. Okay. Now, but if that confuses you, we can just use the formula the way it is. Okay, how about we just use the formula the way it is? Notice that, however, this is important, is to notice that because we're using k plus 2 is defined using k minus 1, there is a difference of 3 terms, which basically meaning that I'm actually going to have formed 3 separate type of coefficient. And everything about it kind of makes sense because you have one that starts with c sub 0, you have one that starts with c sub 1, and then you also have a special c sub 2 to begin with. And that actually likely come from because of the x in the formula. We'll see. So let's start with the following. I'm going to start with k equal to 1. And if I do that, I will have c sub 3. That will equal to negative c sub 0 over 3 times 2. Or I guess I can say negative 3. Well, actually, you know what? Maybe too early for me to use factorial. So let's leave it for now. How about with a k equal to 2? That will give me c sub 4, and that will equal to negative c sub 1 over 4 times 3. What if k is equal to 3? That will give you c sub 5 That's equal to negative c sub 2 over 5 times 4. Lucky for us, since c sub 2 is 0, this would come out to be 0. What happened to k equal to 4? That would be c sub 6. C sub 6 would be equal to negative c sub 3 over 6 times 5. So that would actually equal to c sub 0 over 6 times 5 times 3 times 2. Well, actually, you know what? I'm going to write it in ascending order. 2 times 3 times 5 times 6. What is, when k equal to 5, we actually generate c sub 7. That will be equal to negative c sub 4 over 7 times 6. So that actually comes out to be positive c sub 1 over 3 times 4 times 6 times 7. And what happened when k equal to 6? That would allow me to generate c sub 8. And that's equal to negative c sub 5 over 8 times 7, which comes out to 0. Shouldn't be too hard for you to realize that this is all multiple of 3. So next one would be c equal to 11. That would equal to 0. And then c equal to 14 is 0. C equal to 17 is 0. So forth and so forth. And that basically generate the following term, c sub 3k plus 2, which is equal to 0. I know it's 3k plus 2 because the 3 is basically the difference between each of the arithmetic sequence. So 5, 8, 11, 14, 17, they're all different by 3. And then just to kind of work out the first term, notice that our summation start with 1. So therefore, if I put in 1 into k, I should get 5. So that's why I say 3k plus 2. Okay. Now let's work at these two. So it shouldn't be too hard for you to notice a pattern here. So if k equal to 7, we should be able to generate c sub 9 term. And you should be able to figure out that that should be negative c sub 0 of 2 times 3 times 5 times 6 times 8 times 9. And when k equal to 8, we generate c sub 10. And it shouldn't be too hard for you to figure out that's negative c sub 1 over 3 times 4 times 6 times 7 times 9 times 10. So now come the difficult part. What if I let this pattern continue? What should these two terms be? So the first one is this one have to be c sub 3k because it's 3, 6, 9 and multiple 3. And it's alternating sign, starting with the first one being k equal to 1, because I'm trying to form all these summation using index k equal to 1, because we already have this right here. So I'm going to say this would be just negative 1 to the k, because that will give me a negative term to begin. And all of them have c sub 0. And the bottom would be 2 times 3 times 5 times 6 times dot dot dot. And I just have to figure out how to generate these two terms. They're actually pretty simple. It will be 3k minus 1 and 3k. Notice that this 9 matches this 9. Therefore, if I use 3k, I match the 3k, and then the one before that would be 3k minus 1. That gives you this term. The middle column would form c sub 3k plus 1. See 3k, 3k plus 1, 3k plus 2. Okay, nice little pattern here. Notice that we also start with a negative term. So therefore, I'm going to say is negative 1 to the k also. And this one all have c1, so I'm going to put c1. And on the bottom will be 3 times 4 times 6 times 7, dot dot dot. And so once again, I need the two things that multiply. So it shouldn't be too hard for you to see it's 3k plus 1, which because the last number in the multiplication matches the subscript in our C. So if our subscript is 3k plus 1, our last number in a series of multiplication should be 3k plus 1. And the term before that is 3k. So seem to me that our homogeneous solution is y sub h is equal to c sub 0 plus c sub 1x plus c sub 2x squared, but that term is gone because it is a zero coefficient. So now what I'm going to do is generate the rest of the power. So the rest of the power are formed into three groups: multiple of 3, multiple of 3 plus 1, multiple of 3 plus 2. Okay? Multiple of 3 will match up with c sub 0, and that will form this summation. Actually, I'm going to put the c sub 0 in front. And then you'll have 2 times 3 times 5 times 6 times 3k minus 1 3k. So that would be every term that has a power that's a multiple of 3. So this would fall x to the third, x to the 6, x to the 9, x to the 12, and so on and so forth. I'm going to plus c sub 1. Then I'm going to have the summation k from 1 to infinity. Negative 1 to k, x to the 3k plus 1, so this would be x to the 4th, x to the 7, x to the 10, so on and so forth. And that has a bottom of 3 times 4, 6 times 7, 3k and 3k plus 1. So that gives me the homogeneous solution. That hopefully that wasn't too bad. It's interesting that to note that it actually formed 3 separate patterns in this case, where one of them just go away, which that means we wind up having just two undetermined coefficients, c sub 0, c sub 1, which can now be determined by the initial condition. Okay. And it's a little hard to come up with the multiplication on the bottom, but you just kind of have to know how to deal with kind of arithmetic sequence. So in here would be 2, 5, 8. That would be the sequence 3k minus 1, 3, 6, 9, and so on. That would be the sequence from 3, 6 to 3k. Okay, and when you write out this formula, the slope, technically speaking, because 3k minus 1 or 3k, these are all kind of linear formula, which is basically what an arithmetic sequence is, or arithmetic series is. And so the 3 just the common difference, which is basically the slope. Now let's deal with what happened if we have the non-homogeneous solution, the particular solution. So that will be y double prime plus xy equal to, what did I say? Negative 2x. Ooh, how about I didn't make it too complicated? Plus 3x squared minus x to the 4th. So how do we actually proceed with this? So, well, actually, it proceeds the exact same way and would basically just form the same exact pattern, except that this equation, this recursive formula right here, doesn't always equal to 0, but only equal to 0 at some cases. So let's go and try to not rewrite everything. So what I'm going to do is I'm going to take this equation right here. Let's see if I can just copy this equation right here. I'll go copy. And I'm going to paste it right here. Good. So this this left side is basically what y double prime plus xy is after I re-index and combine and take out parts and everything. So the only thing I have to choose is to change this 0 to negative 2x plus 3x squared minus x to the 4th. So how do we go about doing this? Well, let's start with the following. That implies that this is become 0x to 0 minus 2x to the 1st plus 3x squared plus 0x to the 3rd minus 1x to the 4th plus 0x to the 5th plus 0x to the 6th, dot. So therefore, notice that x to the 0 power would have a 0 coefficient matches c2 times 2 times 1. So that implies that 2c2 equal to 0. So that makes c2 equal to 0. So that stays the same, which is good. So that gives us basically the constant term. Let's look at the x term. The x term would basically be using this summation series, but when k equal to 1, because I have x to the first. So therefore, I would have c sub 3 times 3 times 2 plus c sub 0. And that should equal to the x term coefficient on the other side, which is negative 2. And I'm going to just go over and do a few more just to hopefully see some kind of help me establish some kind of patterns. So x squared would actually be put in 2 for k. So therefore I would have c sub 4 times 4 times 3 plus c sub 1, and that's equal to x squared would be 3 on the other side. X to the third terms would be when I put in k equal to 3, so it's c sub 5 times 5 times 4 plus c sub 2, that equal to 0. X to the fourth term, that would be when k equal to 4, that would form x to the fourth power. So therefore, that would be c sub 6, 6 times 5, plus c sub 3. And that actually equal to negative 1. And I'm going to write out a few more. X to the fifth term, that will be c sub 7, 7 times 6, plus c sub 4, that's equal to 0. X to the sixth term, yes, form a very nice simple pattern here, especially when you try to write them out. I'm going to go through, let's do one more. And then this pattern go on forever. So notice that this one have 3 equations that we have to deal with. And once again, what we want to do is to try to make as many of them as equal to 0 as possible and to find the particular solution. So in here, the first thing I notice is that since c sub 2 equal to 0, we force c sub 5 to equal to 0, because that will mean c sub 5 times 20 plus 0 equal to 0, implies c sub 5 have to be 0. And if c sub 5 equal to 0, notice that if you look further down, that would impact c sub 8 to be 0. And so on and so forth. And it shouldn't be a surprise, because remember, we already established that the coefficients for this particular differential equation form in 3 different sequences. So this is one of the sequences, 2, 5, 8, 11, so on and so forth. So therefore these, I'm going to just say these are equal to 0. So that way, these are all done. What else? Well, let's see. I noticed I have an equation involves c sub 0 and c sub 3, and then I have a second equation involves c sub 3 and c sub 6. And I just have one equation in the middle that involves c sub 1 and c sub 4. So once again, we have kind of the same exact choice here, like in this case, where you can choose to satisfy this equation, right, with c sub 1 and c sub 4. I can either say c sub 1 equal to 3, or c sub 4 equal to something that, well, actually, maybe put it this way. I can either make c sub 4 equal to 0 or c sub 1 equal to 0. And then use the other number to satisfy this equation. So once again, here, make sure you understand the choices that you have to make. So c sub 4 times 3 plus c sub 1 equal to 3 can be satisfied 3 different ways again. One of them is c sub 1 equal to 3, c sub 4 equal to 0. Or c sub 1 equal to 0, c sub 4 equal to, I don't know, 1/4. Or I just basically choose whatever I like with both of them. So once again, this is probably the least useful option, because that would mean that I have to find a way to represent both C1 and C4 together, remember here the best way is to actually make most of them 0. If I do make c sub 1 equal to 0 and make c sub 4 equal to 1/4, notice that c sub 4 non-zero would further down imply that c sub 7 have to be non-zero. And they probably imply that c sub 10 will have to be non-zero, so on and so forth. And that is not a good option, because I will have an infinite list to go through. So once again, the best option here is to make c sub 1 non-zero and c sub 4 0. And that way, I will be able to not worry about the rest of the term, but just have to deal with a finite number of terms. Okay, because if you pick the c sub k that will only affect the equation before it, then you have a finite number of equations to deal with. If you pick a c sub k that's non-zero, that would affect the equation after it, then you have an infinite number of equations that you have to deal with, and you don't want like that. So in this scenario right here, look to me, I'm going to let c sub 1 equal to 3, and c sub 4 would equal to c sub 7, which is equal to c sub 10, and so on and so forth, and they all just equal to 0. So now I have dealt with all of these coefficients, So now I just have to work with, if I'm looking at this correctly, the multiple of 3. So now that would be these two equations. So let's isolate these two equations and see if we can figure it out. So once again in here, the best thing I could do is to make c sub 6 equal to 0, because that would allow me to claim that c sub 9 is 0, c sub 12 is 0, so on and so forth. So that would imply c sub 9 equal to c sub 12, and they all equal to 0, which is good. Remember, we're trying to make many of them equal to 0 so that we don't have to write our infinite series. So if that's the case, that would imply that c sub 3 must equal to -1. And lucky for us, if c sub 3 equal to -1, that will only impact c sub 0, which just so happens we have this equation right here. So let's deal with that. So this equation would only be satisfied when c sub 0 is equal to 4. So therefore, now I think I have my particular solution. My particular solution would have the following coefficients. C sub 0 is 4. C sub 1 is 3. C sub 2 is 0. C sub 3 is -1. And then the rest of them, c sub 4 equal to c sub 7 equal to c sub 10 equal to 0. C sub 5 equal to c sub 8 equal to c sub 11. 11. And they all equal to 0. And then c sub 6 equal to c sub 9 equal to c sub 12. They all equal to 0. So therefore, in this scenario, this combined into my particular solution, which is 4 plus 3x plus 0x squared minus x to the third plus 0x to the fourth plus 0x to the fifth, 0x to the sixth, so on and so forth. So that would be my particular solution. And so now I can actually write out my entire solution. Y, in this case, part C, I guess. Did I label this part B? Yes, I did. So y would actually equal to the following. C sub 0 plus c sub 1x plus c sub 0 summation k from 1 to infinity, -1 to the k, x to the 3k, over 2 times 3, times 3k minus 1, and 3k. Plus c sub 1. Summation k from 1 to infinity, -1 to the k, x to the 3k plus 1, over 3 times 4, times 3k plus 1, plus my particular solution, 4 plus 3x minus x to the third. and I'm pretty good. I just make it about 30 minutes. So I think that would be it. That is the end of 14.7 and also the end of the entire curriculum for differential equation. That is indeed the last video. All right, I'll talk to you guys in during class, okay? Bye-bye.